Hello.
This probe seminar series is an attempt initiated by Academics and Pedagogy team of University Research Center, basically to initiate a meaningful conversation around the content. So far in university, as you are aware, we had a lot of seminars around education and development issues. So we thought even discussion on the content is very useful and we should initiate. And this is the initiation. And I hope this will be fascinating enough. And as who are, I think it's important for all of us to get into discussion on the content, and most of us who deal with teacher education. And hope you also hold the primacy of these kinds of discussions. And today the seminar is initiated by our group members, but hope most of you come forward in future to present these kinds of seminars, and you use this platform to have discussion around the content. And so as you are aware, there are 5 topics that are selected for this round of seminar, and we have one more round in February. And hope you enjoy these 2 days, and I hope many of you will come forward in future to present seminars, especially on the content. So thank you and welcome. And we have many people coming from joined us during this seminar series, and many from our partner organizations are here. To mention, like we have Pushparaj and Kamal Mahindra from Vidya Bhavan Society, and we have Arindam from Homi Baba Center of Science Education, and we have Chandrasekhar from Indian Institute of Geographical Studies, and we have members from Digantar, Kuldeep, Devyani and Vandana, and our field institute members, and even teachers from Valley School and Shishu Mandir. So I welcome you all and hope you enjoy these 2 days. Thank you. So over to Neerja. So this is the first seminar on flight.
Good morning. Good morning, Neerja. Are you able to hear me?
Yes.
Thank you very much for coming to this probe seminar series. And I thought it would be nice if I begin with a little bit of action. I would request my friend, Dr. Krishnan, to just initiate a little action. He's come all the way, and this is a toy which he brought for me. So
this is actually a toy that my son was playing with. And I thought, what better way to start than just kind of illustrating what happens. Before I do anything with it, any guesses what will happen?
Basically, blow this pipe on this balloon, that will get air inside. So once you leave that, so air will come out, that will lead to some turbulent and will just rotate and will move. Something like that.
Okay. Will it do anything else?
To make some sound outside.
Thank you. He's obviously played with it. Okay, let's just watch it. And then we'll do a couple of little experiments around it. And we can kind of understand. I think we can visit this a little later. Whoops.
oh wow.
It's easy to fix. So
Can
what?
I help you?
So all I do is I blow the balloon, as he says. What's your name, sir?
Manish.
Manish. Thank you. Okay, I got it. Now I fix it to this toy right here. And let's do two little experiments, right? One is, I'm going to let it go with the balloon below. See what happens. And then let's turn it around and let the balloon be on top, right? And let's try and understand what's going on. Saw that. So just come straight down, right? And this time the balloon was actually down at the bottom. What do you expect when actually it's on top?
It should go sideways.
It should go up.
No, it will spin, I think.
It'll spin. It'll go up.
Maybe
It'll go sideways.
still come down.
It'll still come down. Why should it come down? Eventually. Thank you. So let's try it, shall we?
You want me to blow?
So, now it's on top. Let's see what happens.
Let's leave that beauty.
So, actually, there is more to this. And this little toy can actually teach you a lot. Let me just leave this observation and let's listen to Dr. Neeraja Raghavan here. And then, I'm sure after your seminar, they will all want to play with this. Okay?
Thank you, Krishna.
Okay?
Thank you so much. Pardon me if I wanted a dramatic beginning, and thank you, Krishnan, for giving me that. I just want to introduce some other members who are listening in to the seminar. Firstly, Dr. Krishnan, 3 decades ago, he was my chemistry student. He was in class 12 when I was his chemistry teacher. And today he is the CEO of a company and we switched roles. He became my physics teacher and I learned something about flight.
No, she's still my physics teacher.
We have Dr. Vasanta Chaudhary, who is my very close friend and former colleague of IIT Kanpur, who is listening in from Austin, Texas, because she helped me a lot in trying to understand flight. We have Ram Kumar, who is a former Air Force pilot, Indian Air Force pilot, and is now a teacher of physics in the school Chennai. And he's listening in on Skype. He also helped me understand the subject. So without further ado, I'd like to get into my seminar, which is all about flight, why and how. Both of you can hear me, right? Yes? Vasu, you can hear me? And Ram Kumar can hear me? Yeah. I think he's offline. This is what I hope to cover in my seminar. Why did I choose this topic? And where was I in my understanding of flight when I started? Who are the key players in my journey? What is the scope of my talk? A brief dip into the history of flight and the explanations of flight that abound. What we were taught when we were in school, and what was the turning point in my understanding in this journey. The doors that opened and some experiments and activities. Can science change? Textbooks that changed. Where do we go from here? Some references. I must confess unabashedly that all through my school years, physics was my nightmare. I had a series of bad teachers in physics. I had an excellent chemistry teacher, which is why I did chemistry. So as a student in school, I understood very little physics and felt it was beyond me. As a first-time flyer, when I was 24, and it was the first time I got into a plane, and I was on a long flight to the United States, and halfway across the flight, I was already homesick and felt like writing a letter to my family. So I pulled out a paper and very dutifully, as I had been taught, I wrote the date and then I was forced to write the place, the location. And I just mechanically wrote what I had heard the pilot just say over the sound system. I wrote somewhere above the Alps. And then I froze. I said, I'm somewhere above the Alps. And I was stunned. This is where I am. And I don't think I finished that letter. But that sense of absolute awe, that I was so much above the ground, has not left me in the numerous flights that I've taken since. And you may say something positive or something negative, but having been a frequent flyer, I never understood flight. I never understood how we were aloft. And this was a nagging question, and thanks to this opportunity given by URC ANP, I got a chance to revisit that question and face my physics nightmare and try and understand at least this one topic. So I'm very grateful for this opportunity. As a middle-aged teacher educator, I steadfastly avoid going into topics which have anything to do with physics, or if I have to, I very openly confess my ignorance and say my PhD is in chemistry, I have nothing to do with physics.
But it has component of physical chemistry.
Pardon me?
It has component of physical chemistry.
Yeah, so physical chemistry I'm okay with, but talk to me about anything which is hardcore physics and I just exit. Now this is where I was when I started. I was convinced that anything that is heavier than air cannot rise. Even if it does, it must fall down with a thud. And when I say when I started, I mean September 2011. As recent as that. That's when I started working on my seminar. My school lessons were on something called Bernoulli's principle, and they honestly never convinced me. I passed my exam and I did pretty well, but it never convinced me. As far as I was concerned, something like air, something so flimsy, how on earth can it support a huge aircraft with people and luggage? I just couldn't buy that. I took my flights and was sure I would fly and come down, but I just didn't understand it. I also knew that we obviously don't fly like birds, so what's the difference? And I wrote down my confusions about explanations that were not intuitive, but maybe they were verifiable at least, so that saved them. Some were not intuitive and not even verifiable. Some had too much math, and a lot had too little hands-on. This is where I was in the beginning, and I actually wrote all this down in my diary saying, I've got to conquer this if I'm going to get anywhere in understanding flight. So I'm going to take you through, not all, but some of my journey. And I would like to request that if there are clarificatory questions, like, 1 minute, what did you mean by that? What is the meaning of this? Please stop me. I'll be happy to explain then and there. But if you have questions of a deeper nature, just park them. The last half hour is meant for that, and we'll go into that in detail. Fell with a thud. It was supposed to fall. So these were the co-passengers in my journey. Azim, whom I was in touch with over email, and I visited his website and did some of the activities there. Dr. B. Krishnan, whom you just met and showed us this lovely toy. Ram Kumar, who's listening in from Chennai. He has flown many planes, naturally, having been a pilot for almost 3 decades. Dr. Vasundhara Chaudhary, who almost became a pilot by her own confession, had to choose in her years in IIT Kanpur, should I finish my PhD or should I become a pilot? She was part of the flying club. She chose to finish her PhD thanks to me, so I learnt from her. And there were many people I corresponded with in NASA, Dr. Thomas Smith, Dr. Klaus Welk. Professor Josiah Brown of Yale University, who sent me a number of documents. I just realized I made a big omission. I forgot to acknowledge my friend and colleague Babu, who's taking care of my sampling. Thanks. So this is the scope of my seminar. All that is in green is what I will be touching. When you talk of aircraft, they could be lighter than air, they could be heavier than air. I will only talk of those that are heavy. In the lighter than air category, you have airships and you have balloons. In the heavier than air category, they could be non-power driven like gliders and kites. They could be power driven, they could be man-powered. I am only focusing on the power driven aeroplanes, not the helicopters. And even this, I am only opening some doors, I hope. I can't do more than that. History of flight was heartening for me. You will find out why. The first successful aerial voyage, I think we've seen those black and white pictures, sketches of a sheep, a rooster and a duck in the first balloon. And then there were these French people, I can't pronounce their names, they set sail in a balloon across Paris. And balloon flight is easy, it's basically based upon Archimedes' principle. And for those non-science people in the background, all that says is that the volume of fluid which is displaced by any body immersed in that fluid pushes it up. So the air which is displaced by that balloon pushed it up, and it was a fairly long ride considering that it was one of the early 25 minutes, and they covered a distance of 5 miles. The hydrogen hot air balloon flew in 1785, and many people tried making toy helicopters. So there was a fascination for flight, and that little doggerel, that verse you saw in the opening slide, was written before we flew. So man always wanted to fly, man as in human beings. Otto Lilienthal in 1895 made the first hang glider. We've seen those pictures where the men actually lay strapped on a glider. Unfortunately, he met with his death when he tried to fly like a bird. And he was a friend of the Wright brothers, who were so affected by his death that they wanted to now try and make a plane. So they piloted the first heavier than air flying machine in the early part of the 20th century. Neither had college education or advanced training, and I was very heartened by that. I said, if two brothers who had not had any college education could first invent the plane, surely I don't want to invent or design a plane, I just want to understand how it flies. So with all my nightmares about physics, I'm sure I can manage that. And both men were self-taught mechanics, and they were trial and error scientists. So this tells you something of their methodology. Now I'm going to briefly revisit what we were taught, and pardon the assumption when we were taught, I think most of us were taught pretty much the same thing. But if you weren't and you were taught the right way, very lucky. We were taught that a wing which is shaped to achieve lift is given a special name. It's called an aerofoil. I'm pitching low in my talk in the sense I'm pitching to an audience who is not familiar with the basic terminology. So pardon me if you know all this. So this is like my rough attempt at drawing such a shape. And we were given this kind of a diagram which said here are the 4 forces. The most obvious is the weight which pulls anything down, whether it's a plane or you or I. And countering that is a force, upward force called the lift. And then there are 2 forces in the horizontal plane, the thrust which propels the plane forward to the engine, and the drag which is the resistance to the forward motion. This is what we were taught as the 4 forces. There was also a kind of attempt at explaining something called Bernoulli's principle with these diagrams, and they were as unclear as this, and the explanations were even more unclear. So I'm going to just briefly describe what is meant by these. Don't worry about the very scientific terminology. Lift is nothing but something which is counter to, is perpendicular to the original flow. So if the gas is flowing like this, lift is perpendicular to that. Drag is parallel to the original flow and it pulls it back. Thrust is a forward force required to move it through air provided by the engine. I'm not defining weight. All of us know what that is. Now, this was what we were taught, but there was a turning point in my understanding because I just couldn't figure out what this Bernoulli's principle was all about. And whenever I read these numerous books and websites, I was basically concentrating on that one force, lift. I said, if I understand what makes something go up, my main mental block to flight will go. So in trying to understand lift, I came across so many different theories. And quite a few of the readings said, if you stick your hand outside a moving vehicle and you feel the air hitting it, you'll feel the air trying to lift your hand. So I sat in one of the Bangalore BTS buses and I put my hand out, and needless to say, the speed at which the buses go, I felt nothing. But I'm going to play this film. This film in the NASA website was my turning point. And I hope for those who are also harboring questions similar to where I was, it will serve as a turning point for you too. For Vasu and Ramkumar, I'm going to advance the film to where the title comes, because there's a lot of unnecessary music and we can save that time. Okay? first time we hear wait.
It is holding.
And then
Hi, remember me? I'm Aloft. I'm an instructor here at the National Test Pilot School. Today's lesson is all about lift, how an airplane creates it and how we can change it. If an airplane is going to fly anywhere in the atmosphere, it's going to have to create enough lift to exactly compensate for its weight. In a nutshell, we can do this with Newton's third law. For every action, there's an equal and opposite reaction. To illustrate Newton's third law, I can use this flat plate with some sort of flow that we can see. For that, we're going to use some water. To provide the water, we enlist the help of the Mojave Airport Fire Department, if you will. Okay, we have a stream of water here, and I can deflect that stream with my plate. Now, as the plate pushes the water down, Newton's third law says the water pushes the plate up, giving me lift. I'm trying to lift the plate and I have to force it down. Now, we can play a couple of games with that. One is I can change the angle of attack of the plate to increase lift. And the other thing is I can change the flow, the speed of the flow, and this momentum. Now, if I increase it a little bit, I get more lift. A lot more lift. Really increase it. There's some huge lift going on here. If we want to get more scientific, we're going to have to use some equations to go from there. Newton's second law is F equals ma, where a is acceleration, the rate of change of velocity. In other words, acceleration is how quickly the velocity is changing. Incorporating this into Newton's second law, we can rewrite it as force equals the mass times velocity change per time. Now, since we know that mass times velocity is momentum, then the second law can also be shown as force equals the final momentum minus the initial momentum, all divided by the time it takes for that to happen. Or basically, the force is the rate of change of momentum. Everything that affects the total force on a wing is shown right here. This is the equation of some force, F, the initial momentum of the air, mass times initial velocity, the final momentum of the air, mass times final velocity, and the time it takes for that momentum to change. Let's determine how we can change the force by playing with each of those parameters, starting with the initial momentum. Consider a ball of air traveling along the streamline before it encounters a plane. This ball has a certain volume, V. We can choose any size volume we like, so let's simplify things and call it the size of 1. More balls are involved as the size of the plate increases. You can look at this along the chord C of the plate or along the span E of the plate. What we see is that the number of air balls is directly related to the area of the plate. This area is given the abbreviation S and is easy to calculate for a rectangular plate. Area equals span times chord. For now, let's just look at one of those balls. The air in this ball has a certain density rho. The mass of the ball is the density times the volume. But since the volume is size 1, well, in that case, the mass equals the density. At first, this ball of air is traveling along with some initial momentum. The size of the arrow shows the direction and speed of the flow. As the air hits the plate, it can't go through, so it slides down along the side. This is a change in the flow's direction when shrinking. We can break this new velocity into two components, one along the original direction and one perpendicular to it. Notice that the new component along the original direction is shorter, meaning the horizontal speed is lower than it was initially. There's also a new vertical velocity that did not originally exist. Because today's subject is lift, let's talk about the change in vertical momentum of the air. Now, as the air comes in initially, it has no vertical velocity, therefore it has no vertical momentum. But as it hits the wing and goes down, it gets some vertical momentum. Now, the change in vertical momentum is simply the mass of the air times that new vertical velocity. This whole process takes a certain amount of time, delta t. Now, from Newton's law, what we see is that the shorter the time is, the smaller the delta t, the greater the resulting force. For our case of looking at the change in vertical momentum, the lift of the ball is density times the vertical velocity divided by the change in time. If there was more than one ball of air involved, then we would add up the lift for each one of them. The lift of the entire plate is density times the vertical velocity divided by the time times the number of balls of air. We now have everything needed to look at generating the force on a wing. Four factors are the density of the flow, vertical velocity given to it, how quickly it happens, and the wing area. Let's demonstrate these effects one at a time.
Well, I'm sure most of you at one time or another in your life have stuck your hand outside the window of a car while you're driving on down the road, and you can feel how the change in airflow affects the lift on your hand. Well, we're going to demonstrate that same idea with the airplane, and this time, instead of driving down the road, we're going to use the propeller to generate some wind speed and demonstrate the effects. Clear prod. Now, I'm using the propeller to create a big slipstream at big velocity past the fuselage, and just like you stick your hand out a car window, there I go with my hand outside the fuselage. Now, as I increase the angle of my hand, the angle of attack, it deflects the air downwards, faster and faster, creating more momentum. Changing momentum causes my hand to lift. As I increase the angle of attack, I get more lift in my hand.
You may have seen this in an air show where the performer suddenly increases the angle of attack to increase the lift and begin to climb.
All right, now we're going to demonstrate the next idea, changing the velocity.
If the air is flowing fast, then it moves from the initial condition to the final condition very quickly, and the time change, delta t, is small. Of course, the opposite is true when the airspeed is low. The transition time is long.
I'll start off with my hand at the same angle of attack as before, and now I'm going to increase the velocity of the air through the propeller by increasing the power. Now, at this higher power setting, I'm getting a lot more lift off my hand. I can push it down more. And just the opposite is true if I go to idle power. Now at idle power, there's a lot less lift, and my hand doesn't get nearly so much momentum.
Now, we've talked about the idea of airspeed changing lift and angle of attack changing lift. We can demonstrate both together as we watch an airplane come in for a landing. Now, the pilot starts off at high speed, but as he slows down for the landing, he's going to lose lift on the wings. So to compensate, what he has to do is pull the nose up to a higher angle of attack to get just the right amount of lift out of the airplane. Now, pilots spend an awful lot of time practicing to get just that right amount of angle of attack so that everything works out very smoothly. Next, we're going to talk about the density of the flow. You've probably heard that as you go up in altitude, the air gets thinner. What we're really saying is the density is going down. Now, if you look at the lift equation, as the density goes down, so does the lift. To compensate, what the pilot will do is increase the angle of attack. Now, if you want to fly all the way up at about 80,000 feet, the air density is only about 5% of that at sea level. So there's no way you can increase the angle of attack enough to compensate for the loss of lift. But if you go back to the lift equation, what you'll see is that you can also increase the airspeed. And that's exactly what the SR-71 does. At low altitude, it doesn't need to fly fast to create lift. But at high altitude, it has to fly fast to keep from falling out of the sky. Now let's look at the last of the four factors that affect lift, wing area. The lift equation shows that this is another way of achieving the desired lift on an airplane. The B-57 Canberra bomber, shown here, could not fly fast, but could carry a lot of weight because the wing area was large. When the same plane was used for high-altitude spy missions, the wing couldn't lift as much because of the decreased air density. That was okay, though, because it didn't need to carry a lot of weapons for spy missions. When NASA wanted to fly the B-57 even higher for research missions, designers went back to the drawing board and came up with a really big wing. The same change in momentum principle can also be demonstrated with the water ski. It's essentially a flat plate that pushes the water down. As the water generates an equal and opposite force, primarily in the lift direction, we'll get lift. Since the density of the water is very high compared to air, you can figure that you don't really need too much area to support this weight of the skier. On the water, a skier needs about 30 miles per hour, and a small ski to support his weight. If the skier goes up to 40 miles an hour, he can kick off the ski and just go barefoot. Not much flat plate area is needed when the density and velocity are high. Let's review today's discussion. We started with F equals ma and showed that the force is equal to the rate of change of momentum. Since today's subject is lift, what we're interested in is the change in vertical momentum. And the lift equation is density times wing area times the change in vertical velocity divided by the change in time. We can play with each of the factors in that equation to show how effective it is. Now, the vertical momentum change is affected by the speed across the wing and the angle of attack on the wing. One other factor that affects it is the curvature of the wing. A flat plate doesn't change the momentum quite as much as a curved surface does. Aero engineers plumb both the angle of attack effect and the curvature effect into one term called lift coefficient. We abbreviate that as CL. CL is just a measure of the effectiveness of the wing in creating lift. And it's really easy to measure in the wing column. Now what we can do is we can take that CL term and add also the airspeed effect to come up with the total change in vertical momentum, which is just the CL times velocity squared divided by 2. You take that, plug it into the lift equation, and come up with the final equation, which is the lift is equal to the density times the velocity squared divided by 2 times the wing area times the CL. Now we can take all of this and plug it into a real-life equation to find out different things about the airplane, such as what is the fall speed for this airplane. So let's go and find out right now what it is.
To predict the minimum flying speed for an airplane like this chipmunk here, we need to know a few things. The wing area is 180 square feet. The weight is 2,000 pounds. And at the altitude I'm flying at right now, the air density is 0.002 slugs per foot. The last thing is the lift coefficient. From our wind tunnel studies for this shape of wing and the angle of attack that it's small at, we find that the maximum lift coefficient, CL, is 1.76. So when I put all those numbers together, can I predict what the minimum flying speed is for this airplane? While you're calculating that, I'm going to slow down and see if I can get this data installed. Okay, here goes. Airspeed is down to 50 knots, 49, 48, 47 knots, and there we go. Installed. So we just established, by practice, our actual minimum flying speed, and our job as flight testers is to compare that to what we have to predict. Well, that about does it for today. It's time to go out and have some fun. This is something I'm going to related.
So this film really was a turning point in my understanding. And I'd like to ask you, did it make any sense? Especially when they show that water on that plate. So then I remembered that as a child in those trains, I used to stick my hand out. At that speed, yes, I remember feeling a lift in my hand. So the first mental block about how can air cause lift, little bit of crumbling of that block happens after seeing this film. I also discovered with a shock that nobody taught me this. They just cluttered my mind with one Bernoulli's principle and said, that's it. So nobody taught me that this is something, it's so experiential. I mean, I'm convinced that this can cause lift. But this was not taught to me. Was it taught to any of you? Just curious. Did anyone learn that this is also a way of lift happening? No. No. I think what we were taught, by and large, was something called Bernoulli's principle. And here is our aerofoil. And we were taught something which today is called the equal transit time theory. We were told that because of the longer path of the upper surface of the airfoil, the air has to travel a longer distance in that curve, air going over the top must go faster in order to catch up with the air flowing around the bottom. This is what we were told. And now when I was reading this, the first question I asked was, does it have a date with the air at the bottom? Why does it have to catch? Had they told each other, see you later, but please meet me at the end. Why does it have to catch? And nobody could answer that question when I asked them. And I'll tell you what happened later. So Bernoulli's principle is cited to conclude that since the air moves faster on the top of the wing, the air pressure must be lower. If you're wondering why must increased velocity cause lower pressure, just wait, I'm going to explain that later. But what I'm focusing on now is that this is what our textbook said. It said air goes faster over the top, so when you've got air coming and hitting that wing, it has to separate because the wing is blocking it. Something is going above, something is going below. That which is going above has to go faster because it has to meet its buddy at the end, and the two buddies meet at the end, and because higher speed on top, lower speed below, so you've got higher pressure at the bottom, lower pressure on top, and there is lift. High to low pressure is the movement always. So I didn't buy this because of my question about whether they have a date. So what was right in this and what was wrong? I went into this a little more deeply, and I discovered, to my horror, that equal transit time theory is not accurate. The fact that this is not generally the case can also be readily observed. Although it is true that the air moving over the top of a wing generating lift does move faster, there is no requirement for equal transit time. It hasn't made a pact with the other wing saying let's meet. In fact, the air moving over the top of an airfoil generating lift is always moving much faster than equal transit theory would imply. We'll come to the why of this later. So where do our textbooks go wrong? That's my focus. I found this in a reference which said, there is no law or rule in physics to require adjacent air before separation to meet behind the airfoil again after separation. And in fact, because air is invisible, if you want to see it, you've got to use smoke. So there were some trials done with smoke. It's called smoke tracers. This is what it looked like. If you look at those little bumps in the dashed lines, those bumps indicate the smoke. So that's where it is before it hits the wing. Okay? I'm going to show you what happens after it hits the wing and separates. Can you see the guys on top have moved far ahead of the guys below? So that it moves faster above the wing is correct, but that it moves faster so that it meets the other guy below the wing is incorrect. So this is experimental evidence saying our textbooks taught us the wrong thing. If your textbooks taught you this, pardon me. So when air flows past an airfoil, the principal misapprehension in the conventional explanation is this. Rejoining is not necessary and does not occur. Now I'm going to try and make this simple to understand. So my target is those who are not science people. Those who are, please tell me if the explanation is convincing even scientifically. You know, if we wish to go upwards, we must try to push something downwards. Like climbing a rope, going up a flight of stairs. We press down on the stairs and that reaction force pushes us up, and that's how we're even walking. It's happening all the time. Are you okay with me till there? Yeah. Now an aeroplane is no exception to this. The wing is so designed and inclined that in passing through the air, it will first attract the air upwards and then push it downwards. And by so doing, experience an upward reaction from the air. If we appreciated that film, we can already see it happening. If instead of water, picture air. Now supposing we have, instead of a flat plate, an aerofoil, how does the airstream change in the way it is affected? These dashed lines are showing you, in very simple terms, without using any science, that aerofoil, that curved shape, is very gently disturbing the streamlines. It's not giving the air a rude shock. Do you agree with me? The flat plate is giving the air a rude shock. So, in my simple understanding, I said for something to experience lift and fly, it should not cause too much turbulence in the flow of air. And one thing which I owe to my friend Basu, she explained it very nicely, an analogy, that just imagine in streamline flow. What is streamline flow in fluids? Imagine the molecules holding hands and going. Technically this is not absolutely true, of course, but I mean there are no hands, but that, quite apart from that, it's not that they are so together. but it's just a way of understanding streamline flow. So it's as if they are holding hands, and then when they hit that wing, they suddenly got a shock. In fluid, streamline flow is the norm. So to maintain streamline flow, how little can the disturbance be adjusted so that streamline flow continues? That's the physics of it, basically. Okay. So if you look at the flat plate, there are these eddies. It's really turbulent. Whereas in the curve, it's neatly going above and below. Now, why does it go fast? We'll come to that. Before we come to that, I wanted some experimental proof that there was really low pressure on top and high pressure below. And I found this diagram in one of the references. You know, these arrows are showing you by their length. They're showing you the magnitude of difference in pressure. That the pressure on top is less and the pressure below is more is indicated by the text. But that the pressure on top is much, much less than the pressure below is more is indicated by the length of the arrows. What I'm trying to say is, on top, the pressure decreases by a larger amount than below the pressure increases. Are you with me till then? Now, we all know that airflow or any force is from high pressure to low pressure. So, the minute there is higher pressure below and lower pressure on top, it's going to feel an upward force. Why does the pressure vary thus? For this, we have to go into Bernoulli's principle. And let me give a simple analogy. Again, this was in one of the books I read. This is called a Venturi tube, and we are talking of air or any fluid going into the tube and coming out of it. But one of the analogies I read was very nice. He said, imagine the London tube, you know, the metro. We can imagine we don't yet have a metro in Bangalore, but imagine a metro in a crowded city. And all the crowd going together into one constriction and then coming out. Okay. Now, if they all have to go into the constriction and come out, so that the same number of people enter as exit, obviously in that constriction, they have only two choices. Either they press into each other or they whiz in that constriction. They go so fast that the same number can be accommodated. Because in a constriction, same number cannot be accommodated. Right? Now, people cannot press into each other, they are incompressible. So we run, we go fast. So wherever there is a constriction, the speed increases in order that streamline flow is maintained. Why is streamline flow maintained? Thus made God air. That's how air is, fluids are. Okay. For those very hardcore scientists, pardon the reference to God. So the fluids have a streamline motion, and this streamline motion demands that when there is a constriction, it moves fast. Are you with me till then? Amount of air entering must equal the amount of air exiting. Now when something moves faster, now look at these molecules. We are talking of pressure in the vertical direction, right? What is pressure? Pressure is the force exerted by these molecules per unit area. That's pressure, right? Now if I'm in a hurry, I'm whizzing, I don't have time to exert pressure this way. Before I can exert pressure this way, I've whizzed through that. I'm one of the molecules, right? So do you buy it that if it moves faster in that constriction, it's not going to exert that much pressure there? No? No. Okay, imagine all these molecules holding hands. They're holding hands and they're running through that curve. First they're going slowly at the entrance, and when they're going slowly there is some bobbing up and down. So the walls are also feeling some pressure. Then as they start going faster and faster and faster, that bobbing up and down happens for less and less time. There's not enough time, they're going to move. So the pressure in that upward direction is going to be less, right? So there is an inverse relationship with
This pressure is from within only, it's not from outside?
No, right now we're not talking of the wing. I'm talking of inside the tube. We will come to the wing. This is a general principle. You can apply it to any flow where there is a constriction. Okay. So now you've understood the inverse relationship between velocity and pressure. So where there is high velocity, there is lower pressure. Okay. Now just imagine, instead of this tube, in your mind, imagine again that aerofoil shape. And the air is all the molecules are holding hands and coming. They're having a nice chat, they come in. They hit the wing. Okay? Now above and below the wing, imagine that it's just like the streamline flow outside. Right? But the minute the wing comes, you've got a constriction above and a constriction below. Of its regular path, which was like this. Now there are two paths. Yahan se constriction ho gaya, yahan pe bhi ho gaya. Right? The minute there is constriction, there is a change in speed. Right? And the minute on top, it's because there's a much greater constriction on top. The curve is much greater on top, so it's gently curved. So the degree to which it affects us is much more on top than it is below. Right? So it's going to whiz on top and not go that fast. Okay? Without equations, this is the best way I can explain. Is it clear? So there you are. I've got now a feel for that horrendous Bernoulli's principle which I never understood. Why there is first of all a change in speed, and therefore why there is also a change in pressure. I must explain that there were so many debates in the readings I read whether the change in pressure is caused by the change in velocity or the change in velocity is caused by the change in pressure. I got so tired of it by the end of it. I said, this is a chicken or the egg question. It doesn't bother me. I am happy to know that velocity and pressure are inversely related. And I read one of the readings which said physicists cannot afford to ignore which comes first. I said, so be it, I'm not a physicist. All I need to understand is why something flies. So for the physicists in the audience, if I'm being inaccurate, pardon me. And we must also make note of the fact that we are making a big assumption here. I'm only talking of aircraft which don't fly at the speed of sound. So like the people are incompressible, they're assuming air is incompressible. They're assuming molecules of air can't get into each other. Which is why they could run in that constriction. Now I found that what is the cause of lift? When I raised this question, I found that there were proponents of two theories. One was Newton's first and second law, which you saw in that film. In that film, was there any mention about Bernoulli's principle? No.
Pressure.
Sorry?
No mention of any pressure.
Yeah, he tried not, but he used those equations. And you don't have to worry about those equations if you got a general feel. So I found there were proponents of, largely in two camps. One camp supported the Bernoulli principle explanation, which said lift is generated by a pressure difference across the wing. When there is a velocity variation, there's a pressure variation. This was one camp. Another said Newton's third law, and sometimes second law as well. They said lift is a reaction force on a body caused by deflecting a flow of gas. That's what our film showed us. And it said velocity variation causes that aerodynamic force upwards. Remember, he talks about the vertical component of the velocity. And I also found some diplomats in science who said, no, both are correct. Sometimes this works, sometimes that works, to varying degrees. What amazed me was, we are flying all over the place, and we don't have one consensus on what causes lift. That's what amazed me. I said, is this science or is this lift? So is it Newton or is it Bernoulli? And I found only one text which referred to the fact that in certain conditions Newtonian theory gives very accurate predictions, and under normal flight conditions it does not give the right answer, and pressure difference can be computed using Bernoulli principle. Basically it's saying both. It's like an astrologer will tell you, you will be okay but you will not be okay, and finally they are right anyway. So when I went into this, I said, no, I've got to get this solved. What causes lift? Tell me one thing. If this is science, tell me one thing. Give me one equation. And I now realized that if I just watched that film more carefully, I would realize that you can't have this one equation. Because if you remember, there's one parameter he's determining empirically there, the lift coefficient. He says we have to do something. He says we have to do something in a wind tunnel and we have to determine this empirically. That itself should have given me a hint that you cannot just have an equation where you plug in or put in all your variables and you get one lift. No, there's something which finally you have to find out in the lift tunnel, in the wind tunnel. Okay? So that depends probably on the material and the shape, so many other things. I don't know. So when I asked this question, what causes lift? What do all the scientists say? You'd be amazed. Some people said Newton's third law, like the film we saw, Bernoulli's principle, second law, also referred to in the film we saw. Then there was somebody who talked about the Coanda effect, which I have not understood, but it said lift is generated by the viscosity of the air. Then there was the scientist Thomas Smith. He has a website called physicsmyths.org, MYTHS. So he said lift can never be generated by viscosity of the air. So I said, okay, I wrote to the guy who talked about Coanda effect, Dr. Weltner, Klaus Weltner, a German, and I sent him Dr. Thomas Smith's paper. I said, what do you think, sir? And I took Dr. Klaus Weltner's paper, Coanda effect, And I sent it to Dr. Thomas Smith. I said, what do you think?
I have not followed what you said by viscosity of air.
Don't worry, I haven't followed it. I said, before I understand it, let them explain it to me. So I said, what does it mean? Viscosity is basically thickness. Okay. So I asked each of them, I said, please see your paper and explain it. I'll tell you, a very interesting thing happened. This is just a quote that even, quite embarrassedly, NASA also acknowledges that there is this kind of a debate. 100 years after the first flight, we are still debating and various explanations are put forth and the debate is still going on. Believe me, it's still going on. So here's what happened. My electronic correspondence with both the scientists. I'm just reproducing one section. Smith said, I know this reference you mentioned, but even though they make some valid points there, they're actually incorrect. Well said that I did not succeed to understand the paper he cited. There is some confusion in the argument. So then I said, if Weltner doesn't understand Smith, why should I? I don't have to understand. Then I said, no, let me just ask Smith, because he's proposing a theory. So let me ask him, is there a simple experiment I can do to convince myself of your theory? Then I'll try and understand the theory. I didn't tell him I haven't understood it. So I asked him and he said, yeah, sure. You can do this experiment. Take symmetric and asymmetric shapes, place them in a flow of air. And if my theory is correct, and he's sure he's correct, he said, you don't even have to do the experiment. I know I'm right. A difference in weight should be seen only for asymmetric shapes. Simple enough? This is where I roped in my former student and friend, Dr. Krishnan, and said, let's do this experiment. And I got this wind tunnel made. I got all these shapes made, symmetric and asymmetric. Went down Bandargata Road, found one guy who does works with tin and said, make these things for me. And then we actually tried it. This is what we did. I had this wind tunnel made. We placed one of these shapes on an electronic balance, and before I did this, I had the experiment design approved by Dr. Smith. I sent him a diagram and he said, yeah, this should work. And without the fan blowing, we noted the weight. With the fan blowing, we noted the weight until it stabilized. We turned off the fan just to make sure nothing had evaporated and then took the weight away. So this was our experiment. Here are the pictures. Here are the shapes. You can visualize it. You can see the fan in the first picture, the back. You can see some blades of the fan. Yeah, that's the fan. This is the wind tunnel and this is the shape. Here are our results. I'll give you a second or two to look at the results. You notice in the first column, weight before turning the fan on. No matter what the shape, there is some weight, which seems to drop once you turn the fan on. And once you turn it off, the weight more or less comes back to where it was, plus minus 1 mg. Can I move on to the next slide? So what was our conclusion? All the shapes seem to show a lower weight. But then we said the instrument error is probably 1 mg. So if that is the case, the symmetric aerofoil did not show a change in weight beyond the error of the instrument. But the symmetric triangle, now when I'm saying aerofoil, I mean the curved shape, and when I say triangle, I mean this. This is the symmetric triangle. It did show a change in weight. Asymmetric shapes showed a change in weight whether they were triangular or aerofoil. And it was beyond the error of the instrument. So it didn't prove anything to me. It didn't prove Smith's theory certainly, but it was very exciting to see that weight could change, even if it was by a small amount. Just by putting some air behind it, that weight could change. We had fun. Christian's kids and I, we had fun. So then I wrote to Dr. Smith, I sent him my results and everything, and I said, here you are, these are the results. Here is his reply. I appreciate the effort, but he gave me various suggestions on how to prove him right. You should do this, you should do that. Which is fine. I mean, he has every reason to suggest how his theory can be proved right. But then a new question popped into my mind. I said, if this is all that needs to be done, how come he hasn't done it till now? How come he hasn't put any of his graduate students on the job? Can a scientist be so sure of his theory that he doesn't have to do any experiments to prove it? There's a story about Einstein. I don't know how far it's true, but when there was an eclipse, a total solar eclipse, long after he had proposed his theory of relativity, and the only experimental measurement that could be done was during an eclipse. So there was a lot of hype and all the reporters were getting very excited that they were going to finally find out whether Einstein was right or he was wrong. So all this hype was going on, in the typical way some reporter went to Einstein, I believe, and said, "Sir, so what do you think? Supposing you are proved wrong." So he said, "No, I won't be proved wrong, it's right." So they said, "No, but just suppose you are proved wrong." He said, "If it is proved wrong, I will be sorry for God, because I know that I am right." So when it comes to Einstein, because of whatever aura around him, we can laugh and say, "Wow, he was so confident." But I wasn't able to feel so sympathetic to Dr. Thomas Smith. So I said, what is science? Can a theorist be so sure of his theory that he needs no experiment to prove it? I am quoting his first email to me. "If you have the time and means to do such an experiment, I would be very interested about the results. Not that I question my theoretical arguments. But it is always good to have an experimental verification." I wanted to ask, but why don't you question your theoretical arguments? If you are truly scientific, you should. And you should be open to others questioning your scientific arguments. So there we are. There are more and more people who say we still have all these polite fictions about how wings work. So I said, okay, if all the scientists are battling, I'm going to sit down and say, what are the explanations I'm most comfortable with? And I'm going to say, this is what Neeraja Raghavan believes. If everybody has got their view, let me have mine. So this is what I'm convinced of, that lift can only be produced by the wing when the flow of air is smooth. I'm again reproducing a diagram you've seen earlier on the right, and on the left I'm just showing in a diagram what that film told us about the vertical component and the horizontal component. So I'm somewhere between using both Bernoulli's principle and Newton's laws, and both of them seem to satisfy me on what causes lift. But wind tunnels are needed to calculate lift coefficient. So everything doesn't come out of the theory, something has to be done experimentally. So this amalgam satisfies me. And now I revisited where I was when I started. Convinced that anything that is heavier than air cannot rise, that went away. My school lessons, yes, they didn't convince me, but now I was okay with Bernoulli's principle. Air can't support anything. No, I'm okay now. Air can. We don't fly birds, so that I still have to investigate. And in my conclusion, not intuitive, but verifiable, that went away, because I did verify some things. Not intuitive, not even verifiable, that remained. Maybe Smith falls in that category, I don't know. Too much math went away, because I felt without math I was able to get this far. Too little hands-on. I said, now I better do some hands-on. So what causes lift? I went to Arvind Gupta and I said, give me, because he is the hands-on guy. I said, tell me some hands-on thing I can do. So he gave me this suggestion, and I'm going to produce a less than 1 minute video to show you what I did. I must acknowledge Valley School KFI Bangalore. We use their lab. What you just saw was the shape which flew, which went up, which rose up when I had a stream of air fall on it.
I want to. Why not? It's going on. One more time.
The fan is here. So that was nice. We did another one. I wanted to do one with this. This was Kapu's idea. She said, if shapes make a difference, why don't you do something with a different shape, and this shouldn't rise so easily as that. That's indeed so. So here was a surprise. That's science for you. Reminded me of there's a joke, I'm sure you've heard it, about the bumblebee. According to the principles of aerodynamics, the bumblebee should not be able to fly. The bumblebee does not know it, so it flies. But this guy didn't know it, so he went up. So anyway, to set aside the joke. I asked Azim Gupta, I said, how come? So he said, look, until I see how you did that experiment, I can't answer that. So I'm hoping he will recover and I will show him the experiment and find out. So that was that. So I got some hands-on experience, and I also went about making these which you're free to try, and also Krishna's toy which I saw only today. We can play around with that. But these things helped me to again break some of my mental blocks about flight. I actually got my hands dirty. So even a simple flat plate, it can turn air, just as we saw in that film. So I said, look, anything that turns air will fly. Okay. Obviously a plane can also do that. And any physical body moving through fluid can create lift if it produces a net turning of the flow. The factors that affect turning of the flow. Now I started asking myself, what affects how much air is turned? And before I show you, let me ask you just what do you think? What do you think affects how much air is turned?
Maybe the surface area has to store.
Something to do with the object. The surface area, the weight, the blah blah blah, the thickness, so all to do with the object. Anything else?
The speed.
The motion. So the motion, how fast it's going, the angle at which it's, so all to do with the motion. What else? You've got object, motion and air. The air itself, properties of the air. These are the three players in that drama. The object, the air and the movement itself. Okay. So happily enough, yes, this is what the NASA website says. And I don't think I'm going to have time to go into detail in each one of these. But now I came to a point where everything can be tried out in these little toys. If that was so, we can all design planes. So it's quite a complicated thing. And instead of doing it by hand, NASA website has some lovely Java software simulations. I did vibe with one of the examples given in one of the readings, which said, when high-speed cyclists, what do they do when they want to cycle very fast? They crouch. So they're reducing their own area so that they feel less resistance from the air. So that makes sense. That means if something is big, it's going to experience a lot of drag. But if you remember our film, if something is big, it will also experience a lot of lift. Right? So the pilot's game is this, that lift to drag ratio, L by D, is what they are constantly trying to play around. They want maximum lift and they want less drag. And when they are landing, they want more drag and less lift. So cycle example helped me understand drag. And of course, the greater the speed, the greater the drag. But the greater the speed, remember, greater the lift also. So what are the factors which affect lift and drag? Both of them are affected by the same things. The object, which we said, could mean things like the geometry, the size, the shape. And what is aspect ratio? When you've got that shape, it's that distance by this distance. Okay? You've got a curve. The motion, like the velocity and the inclination angle, and the air itself, the mass of flow, the viscosity, thickness in simple English, and compressibility. NASA website has this lovely, I'll just show you this, and we can't play around, but you can do it at leisure. You can actually move these things. You can move the slider bar and you can see what happens. See? So, even if you don't have to actually solve the equation, if I can do something as simple as this and look at what happens to the lift, it's good enough for me. Getting as hands-on as I can get into something which is so technical. So like this, there's a lot of lovely software on the NASA website. I found it one of the best for understanding flight. What do we mean by the size of an object? Something as cumbersome as a plane. What do you look at? The size of the wings or the tail or the nose or the head? Size means what? Sorry? Entire. But that's true. That's true today. Initially, what it meant was the frontal area. This is my clumsy attempt at drawing a plane. The nose is facing you. So by size in those days, they meant just that much. Okay? If this were to go like those Tintin comics where they go and fall flat. So this was to fall flat. This is the only area that you look at. And large bodies have more drag and more lift. Again, this is another such site where you can play around with size parameters to see how that affects lift and drag. Like the other force drag, the lift is directly proportional to the area. Doubling the area doubles the lift. It also doubles the drag. So these two are constantly fighting these up, lift and drag. When you have too much of an angle, that's also a problem. Because then you are disturbing, you are being rude now to the stream of air. You are not being gentle in disturbing its streamline. So your streamline is gone, it's turbulent. So the angle can go only so much, and if it goes beyond that, it does affect the streamline. Velocity, very nicely shown in this, that is a speed square law. You square if you double the speed, you square the resistance. Resistance is holding bodies back by corresponding forces pulling the bodies forward. Number of men shows you the force. Both lift and drag are proportional to the square of the velocity. The air itself, it makes sense that if it's more dense, then it will produce more force. There are more molecules hitting against the wing, so there will be more force. Again, there is some very nice software which I am not going to show you now. And similarly, factors affecting drag are, I don't think I have time, but there's a very nice podcast, I can share the link with you later, which explains very nicely how drag is affected by different factors. I found something interesting, that science can change. What you said was that size means the whole area. That is true today. Why is that? When bodies were badly shaped, that frontal area, the smashed skin thing was enough to think about the size. But today, because streamlining airplane design has led to skin friction playing an important role, we've become better at designing planes. So now we have to change our equations. We have to take skin friction also into account. So it means it's called wetted area. Everywhere where the air washes over, that's the area. Textbooks, of course, can change. We wish they did. Otto Lilienthal explained the aerodynamic lift. Apparently, according to one of the references which I give here, initially they had the right explanation for lift. Somewhere this error crept in, equal transit time theory. They even give a date here. I found this very funny. It was necessary that the explanation of lift using Bernoulli's law had to be complemented by giving a cause for the highest streaming velocity. It reminded me of when I was a child and I would ask my mother, why this custom, why that custom? She would feel it necessary to come up with some reason for that. So I didn't see much difference between that and science. So the wrong hypothesis crept into our textbooks at some point. So I was thrilled that just by choosing this topic flight, so many epistemological questions also came up. So I'm revisiting finally where I was when I started. That's all that remained. Not intuitive and not verifiable. Where do we go from here? This I have to show you, because now I got so interested in flight, I'm planning 2 more seminars. One on bird flight and one on pedagogy of flight. And these tele-serials show you a little bit so that you'll come and tune in next time. So when you come to my next seminar, I'm going to show you this. Bird flight being as beautiful as it looks, I learned that there's a very different science. Some of what aircrafts do, but what birds do, we still haven't understood a lot of it. That's going to be even more exciting to understand. And feathers, I was very fascinated to find out that they have a greater strength to weight ratio than any man-made structure. And birds are equipped with excellent excellent eyesight, no other living being can match their visual acuity. This is a very nice book. And future seminars, I hope, will be on these two topics. These are my lectures. Thank you very much. I can take questions. Yes.
I want to start with a couple of comments.
Yeah.
The highest compliment I can pay anybody, because I'm also a teacher, is to tell you that you are a kid with a great delightful vocabulary.
That's
So, to me, a kid is the ultimate goal. So, what is interesting about what you also said is that I know of this thing, we know of these things, basically living in juice. At heights, we should not be at, and we don't know how it works. Serious, huh? Next time I try, I'm going to be very afraid.
I'm sorry if I've done that.
No, not at all, not at all, I'm just kidding. But for me, a very practical question is, this same kind of approach to understanding is, the methodology is absolutely fascinating and very, very delightful. The pedagogy is also equally very, very powerful. But how do you convey these to teachers of schools where their idea of teaching job is 9 to 5, have a stick in your hand, keep the kids quiet in class. That is the ultimate end of the day. How do you convey this kind of excitement? I am struggling with that kind of issue in another subject, but I'm curious to know what your thoughts are.
I'm also struggling, and I wish I had one ready-made answer. The only thing I can say is when you get excited, you infect others. The more excitement you show, hopefully out of 50 people, one person will get excited. But the converse is definitely true. If you show no excitement, you can be sure nobody will be excited. So I think that I'm sure of. The rest I'm not sure.
You'll be turning out the potential for excitement in a larger number of people.
Yeah. That's about all I can say.
Thank you very much.
Thank you. Yeah, Ram.
I don't know whether you're going to handle it in the third seminar.
Yeah, no, never mind.
But I stopped teaching physics because of this. I was quite excited as a student of physics. When I started trying to teach physics, I was like totally stumbled. And I didn't want to teach wrong stuff.
I know.
So I switched to mathematics.
Okay.
How does one teach physics?
Come do some seminars, you can learn physics.
The same Arvind Gupta's experiment, same thing happened. I said I didn't know how to answer.
The risk of overstating it, I think all the questions that come in everybody's mind, I think the first rule of thumb is to admit that those are valid questions.
Yeah.
I think that is where the problem arises, where the teachers dismiss those kinds of questions when a kid says, oh, why doesn't it do that? Why can't human beings fly? It's just a natural question.
Yeah.
But I think if you really dig deep, actually all the answers are here. I mean, it's very obvious why we can't fly. But the point is, the question is a valid question. And just to recognize it, confront it, and really show experiments that prove or disprove is the way that one can actually demystify this. Right?
Yes.
But what I try to say is even after quite a serious amount of search from someone like you, still
there are many gaps, sure.
So, but the textbooks on the other hand make it
opaque.
Opaque. And at the end of a large discussion, the students also are left
Lost.
Yeah, what did I do with what
Don't
I
you think we can take students through such a process?
No, I'm asking why teach physics at all.
That's outside the scope of all my seminars. I don't know what I was never taught physics. Yeah.
Actually, I think this question of why teach physics at all probably leads us to the question, what do we think physics is?
Yes.
Because I think we have very different perceptions of what physics is, and that's part of the problem of teaching physics and science as such. I mean, listening to Neerja's narration of this whole debate about flight, etc. I think she started very well with that, the diagram saying that there's so many types of flight, and I'm going to concentrate on this and that. Even in each particular example, the actual dynamics of what is going on
Yes.
is far more complicated,
Yes.
while we tend to simplify it.
Yes.
But you know, the interesting thing about history of physics is precisely that you know, when we were trying to evolve theories from empirical observations and trying to, you know, justify theories only that would explain empirical observations totally. Philosophers of science tell us now that we were basically in the Aristotelian age, and that it is only at a stage where, well, they attribute it to Galileo, and there must have been other philosophers who probably realized this, that you know, nature is far more complicated
Yes.
than what we assume it to
Yes.
be. And one will have to idealize actual empirical observations to even recognize some of the fundamental relationships that are revealed to us in very complicated phenomena. And that is what Galileo talked of, you know, idealization of, that you can only try and explain the phenomena, that Newton could reach his laws only by assuming a point mass, and that if you try and explain the complexity of an actual three-dimensional body, it involves too many numbers of freedom or degrees of freedom or too many variables to explain. The problem is when we try to convince everybody that physics has answers to all these empirical situations, or that science has answers to all these.
The problem is that's how we are taught.
That's how we are taught,
We are
unfortunately.
taught as if science is your sab kuch samjh mein hai. And the appalling thing was in my MSc, when I was in MSc, I got a root shock that science does not have all the answers. As late as that. And it was such a crushing disappointment. I'm not going to get all the answers from science.
And yet all those fundamental principles that some of the great minds have discerned out of that, you know, large mess of empirical observations are very fascinating. You know, how that simplification leads us to such understanding.
Sorry.
Yeah. But just to finish, you know, it's interesting because there are so many such examples. I mean, the candle experiment in which why the water rises is one of these classic cases. And interestingly, you know, you look at literature about 100 years old, you find people were, you know, trying to explain those things in a more complicated way. And then suddenly somewhere in the history of a textbook, somebody thought, here is this experiment which, you know, very simply shows that oxygen is 20% part of air. And the whole tendency, you know, that somebody put that in the textbook. Then we had the cut and paste culture that, you know, amplifies these oversimplification at times wrong concepts pervading the curriculum. Neerja, I must thank you for.
Thank you.
Very brilliant.
Thank you. Yes, Karu.
Just a slightly different question.
Yeah.
In your journey of discovery,
Yes.
Was there any reference to temperature? Because
Not as affecting flight, but it told us,
T1 equal to T1 over T1 equal to T2 over T2.
Oh, those gas laws.
Yeah. So you know, temperature at the higher, on the upper end of the surface and lower end of the surface. If there is a difference, what happens?
Not between the two surfaces. There were references to how the temperature changes across the layers of the atmosphere, and it's funny, it reaches some plateau at some point. You know, when we fly, they say the temperature outside is minus 57 degrees Celsius. Immediately they tell you this horribly freezing temperature. So that's all the reference was, but not to temperature as a variable affecting list. No, that wasn't.
Yes.
At any point, you know, during this journey, did you think about actually explaining what these guys who make airplanes have to say about how they fly?
You know, actually I wrote to NASA. I said, can I correspond with your scientists? Because I'm, you know, really very bemused by this plethora of explanation. They replied and said, we don't have any experts who will correspond with you. Here is our website, go to us.
And when I'm talking NASA, the guys like Airbus and Boeing, who every day tell us that here is a new plane that flies better.
Well, actually, I wanted my friend Ramkumar, who has been an Air Force pilot for 3 decades, to repeat what he told me yesterday. It kind of addresses your question. Ramkumar, do you mind just repeating what you said yesterday about And I'll put the mic to you.
No, what?
One. Ram, can you talk? Just testing. Can you say something and let's see if we can hear you? We can't hear you. No. Okay. You say it and I'll repeat it. Yeah, say something. Testing.
It's on.
I can hear him, but now when you 1 second. Yeah. Say.
It should be better now.
Yeah, we can hear you. Yeah. Say it.
Is it better?
Yes. Yeah, it's fine. Yeah, Ramkumar, please go ahead. Say
Okay, what?
You're on. Yes, Ramkumar, you're on. Please say. Say, Ramkumar. Ram, can you hear us? Ram, can you hear us? Now you start talking and putting you on the mic.
Can you hear me?
Yes. Please say. Yes, we can hear
Again,
you.
you can just read out what I'm saying.
Okay. No, we can hear you. You just say it. You don't have to type. We can hear you.
Field of mechanics, fluid dynamics is one of the most complicated. And in that field, particularly gas flow is more complicated than liquid flow because there is compressibility, there is humidity, and there is a whole range of other factors that come into play. And that's what makes this field so dynamic, fluid, and unpredictable. And if this 28, 29 years that I've spent in this field, it has been a story of adventure and a love story simply because of the complete unpredictability of it. One day one thing, another day a different thing, and it's awesome when you get into this ocean of air. That's what keeps the awe and the wonder and everything alive. And I think that it is made for the fact that one has a great deal of respect for nature because of this, that it's completely, one can never say that one has understood everything completely. And it also brings in a great deal of humility with which you approach, because, you don't know everything. That's what I wanted to say.
Thanks, Ramkumar. Thank you very much.
Just want to add.
Yeah.
I just want to add one little thing. That if people understood, if the Airbuses and the Boeings really understood flight very well, it should not be a big deal to move from a 350 to a 380 or something like that. But the amount of tests that they run through before they can actually produce the empirical data to understand that in fact it does do what we want it to do is just mind-boggling. And the total quality cycle that it needs to go through to actually prove and consistently reproduce the same performance is, I think, it's fair to say it's an inexact science without overstating it. And I think it's just right in tune with what Ram Kumar said.
This PAT Airbus, now everything cracks, which they didn't anticipate.
Exactly.
They are going back.
It is.
To the drawing board.
Do you have any other questions or comments? Yeah.
First of all, I would like to thank you for the whole explanation. This is not very much related with the topic which we are discussing. I just was wondering, why you have not started with the, let's say, the natural creatures, like birds and all. You are taking the taking it in the second series. I guess the similar, the principles of flights are operating behind the whole flight mechanism in the natural creatures also. So this is very obvious to analyze those. And then we are coming towards the man-made.
Why this order?
Yes.
Question is why.
Yes.
Simple question, simple answer to that is, I want to understand how I fly first. So I'm going to begin there. When I get into a plane, how come I'm up there? So that was where my starting point was. Yes, equally valid could be a starting point how do birds fly. And while there are some similar principles, there are many different ones. So when I do that seminar, please come.
Also,
There's a question here.
Thank you for this wonderful seminar. I think there's another important issue which you touched upon.
Yes.
Is the textbook analysis.
Yes, yes.
In the sense that you said that the Otto's explanation early in 1920s, till then the explanation was almost correct.
Yes.
And then suddenly this equal transit time theory came up and giving wrong explanation. So could you give us some account of how did you go about the? I mean, I have two questions in my mind.
Yeah.
One is how did this change in the approach to teach flight in the textbooks came up, number one, and what happened in the Indian context, in the Indian science textbooks context, and I mean, did you do some kind of textbook analysis and in that going to the history of how was this being taught and something like that?
My answer is I have not yet done any textbook analysis. I have simply gone by the common feeling amongst people who were taught flight like me in school and my own school experience and my recollection of my textbooks. I have not read a single textbook today to check whether that's what they say today. But I did have some confidence in what I'm saying because almost everyone I talked to, and I talked to a number of people on their understanding of flight, they said this is what they were taught. In fact, even my colleagues here, when they saw that film, I think, am I right, Basu? You said you were never taught that, what that film showed. She said that. So this is what I went by. And what you're suggesting is a very interesting exercise. One can do that. But I'm more interested in just correcting the wrong thing. And then, we can analyze how did that error come in and so on. Sure.
But then there is the other question also, that we are not talking about English language textbooks.
Yes.
The terminology, the concepts.
In the vernacular, I don't know. I have
so even more problematic, I would think. Yes, and therefore, very important to do the textbook analysis to see what they're doing in non-English language.
It's a worthwhile exercise. Yes, Neeraja.
But I thought even more important than that was to convey the idea to children that the textbooks are not everything, and there's a world outside, and there are experiments, and you can verify what is there in the textbook, and you can come up with your own theory, and you will not be wrong. You will also be equally respected. That is the idea that I think she's gone like a child from the textbook to an experiment, and like you talked about the pedagogy, that's what a child should experience in the classroom or outside.
So it's a very interesting point you bring up, because much as one would like to codify it in textbooks, very often you never, typically when a scientific paper is published, it first is refereed and put in there, right? And then other kind of body of work start building around it. Only when a significant amount of body of work is actually built around it, do they actually make it to textbooks, if you will. So there is a factor where one has to kind of basically say, okay, are you really confident of putting it into a textbook? So there's a...
But obviously that didn't happen here.
Correct. That didn't happen here because there's still a... For example, today, fluid dynamics, I don't know how many people have thought about this. We cannot create a cloud in the laboratory. Just think about it. We see clouds left, right, and center, but we cannot create a cloud inside a laboratory. I haven't seen an experiment that actually demonstrates that. So, simple like that.
Can I just make a couple of comments on the textbook issue?
Yeah.
There are two problems involved in textbook development. One, of course, is that any textbook development exercise, unfortunately, is a very time-restricted exercise. And I've been to a number of those exercises now, both at the national level and state levels. The best that any team of textbook writers can do is to look at other textbooks, other sources, and put them into. They don't have the time to verify even their sources. So one can see how this, that's so sad. One can see how this amplifies these sort of distortions. And the other is to, develop a well worked out pedagogical exercise around even one particular topic. It is a huge research exercise in itself which we don't acknowledge.
Absolutely. Ram and then Nisha. Nisha and then Ram.
So, regarding this flight, I have one doubt. How does this position of the flight, sometimes it's like runs horizontally and it takes this immediate flight. So how does that affect me? How does it help?
If you've understood in that film how that angle of inclination affected the list.
Okay, yes.
You saw that, right? So nowadays when I fly, previously I used to ask when I got my boarding pass, please give me a seat which is not over the wing because I want to see the view. Now after doing the seminar, I said, please give me a seat which is near the wing. Because you can see the shape of the wing change if you observe. So little flaps खुल जाते हैं और वो जब ऊपर चला जाता है ना, wing becomes flat. The shape of the wing changes. एक बार जब ऊपर जा गया, हो गया, then it doesn't have to lift anymore. No, it just has to cruise. So then it doesn't have to have any angle. So angle तब चाहिए जब उसको ऊपर जाना है. That's as
so when the flap opens,
you just look at the shape. There is a curved shape when all the flaps tilt at a particular point. By the time you reach a certain altitude and say, okay, the pilot has turned off the seatbelt sign, but for your safety, blah, 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 blah. That time you just look at the wing, it's flat.
Then what symbol in that formula shows this? That
angle of inclination. Excuse me, angle of inclination.
I might have.
Formula we can do what?
Angle of inclination and the area. Because the
area will change.
The ailerons.
Those little flaps, they change the area.
The aerodyne changes.
Yes.
You said the wet.
Yes. Wetted surface. Yes, Syed.
Comfortable flight. Flight when slave mode, the cockpit area.
Sorry, start again the doors.
The flight is when airborne. The cockpit area is little higher than the tail area.
Not always. Okay.
Whenever it's flat. And when it's landed, the back area touches. Turns down the first, then the front area.
Why is that? Are you asking why? I really don't know the answer. Maybe our pilots may.
I think what Neerja has explained, can give some of the answers there because it's all about the reducing the angle, right? At that video, it talks about that you have to maintain the angle so as to have a smooth land. That cannot have any
The plane lands
very smoothly. You remember she said about the fact that the drag increases when the surface area is more. So which is the surface area that's more? This way or this way? This way, of course, you don't want to do it because you will crash right now, right? But you can go this way. Then that way you actually have more drag, and then you come down.
So if you land with your nose wheel down first.
No, Ramkumar, the question is why do we land with the bottom wheels first? Or do we always land like that? That's what's called
point landing.
1 minute.
Bottom down, do you mean the rear wheel first?
Yeah, that's the assumption. Rear wheel first.
I'm just giving you also one.
Can you repeat the question? Hello?
Yeah.
Can you hear me?
Yeah, we can hear you. The question is why do planes usually land
first? Do we mean the rear wheel first?
Yes.
And then the nose wheel later?
Yes, Ramkumar, that's what we mean. Is that right? Can't hear us.
No. It's against me.
Have a positive angle of attack when you are flying. And as you slow down the airplane, the angle of attack has to increase so that sufficient lift is generated to keep the airplane flying. And therefore the airplane has to be nose up even when it's coming down. And therefore the rear wheel starts first before the wheel.
Thank you. We needed a pilot to answer that.
First of all,
sir.
Also, you wanted to answer that question?
King, but I know that the left is also with the nose up. So I let the others respond, but I have I have a remark to make, but I can make it later.
No, you can make it now, no problem. Go ahead.
Okay, what I was saying is we still haven't figured out, Neerja, in our conversation as to what is the proportion of lift from the air turning the versus Bernoulli. And I haven't spent time, but I want to find the answer to that.
I know, you asked.
The textbooks talk about Bernoulli because that is the topic they were talking about. Actually, they were trying to explain why the plane flies. They were trying to explain one part of it which makes the plane a little less heavy when it is airborne. The lift you get during takeoff because of the inclination is an important part of taking off, but it is not an important part of staying in flight.
Yes, but I still haven't found the answer to that question. In fact, after you asked me, I tried to look for an answer, but I'm still looking.
Okay.
Yeah, Chandrika.
I had this question which we had also, when we were traveling together, we did ask each other this question. So when we take off and we land, they always ask us to keep the windshields open.
Yeah, somebody answered that. You asked that and we said right. Somebody answered that. Why do they tell us, please keep your shutters up, don't put it down? Ramkumar, do you know why? When we are in a plane, they tell us, now that we are going to land, please make sure your windows are up, don't have them closed. Security. Security reasons. If there's an accident, they want to be able to look inside. Yeah.
About the bumpy rides, sometimes during the monsoon particularly, we find that the plane is dropping somewhere and then again.
Turbulence. When the air is not, sometimes you get into an air current where there's a lot of turbulence, weather conditions, whatever. So then you're streamlined, the molecules are not holding hands, they're still not. That's the problem.
Is there any water gap, air gap or something like that?
Not air gaps. The air currents are no longer streamlined at that part because of there are pockets of different currents. So you are experiencing that. Usually weather conditions.
How does jump jet work?
Pardon?
Jump jet.
Yeah.
How does it work?
Jump jet is outside the scope of the seminar. I haven't studied that. I will. I'll come back to you. I haven't studied jet.
The helicopter also would be income.
Helicopter is not possible. Anything else? Yes.
First of all, I would like to congratulate you. Actually, you conducted really neat teachers in everyday life, but we find that such curiosity is really missing.
Yeah, but have you finished?
Yes.
My answer to that would be, again, to relate an experience from my life. When I taught science to class 6 in the Krishnamurthy Foundation School, Chennai, and that was the first year we had physics, chemistry, and biology. And physics being my nightmare, I did a lot of homework before I taught. Biology, I was zero, I had not learned biology. So I took home Attenborough cassettes and I watched them and I taught them and it was fun. Chemistry, I said, you wake me up from sleep and I'll teach you so I don't have to prepare. So at the end of the year, when I asked them which was the most exciting subject, what do you think they said?
Physics.
Biology. Wait, when I asked them which is the most boring subject, what do you think they said? So this curiosity, obviously I had lost it in chemistry. So I had this curiosity because I had chosen a topic for my seminar where I'm truly curious. I don't know. This I know, that is the worst bad. I know. So that curiosity goes. I don't know has to come.
But actually, I was thinking on a different line. This particular seminar has implications for teacher education.
Absolutely.
And I believe that a teacher should not be coming into the classroom with...
Absolutely.
So,
absolutely. But what I'm saying is, this should becomes natural if the teacher is teaching something which they don't know. The minute I know something, my curiosity has already taken a backseat. I know it. That's the problem. Yeah.
I would like to, this thing is coming quite often about experience. You're more as a physics student. I love physics. No doubt. But I see that even the round there is this question that why do you want to teach something? So to me, this curiosity cannot arise in the classroom only due to teacher. It has to see that whether the child has some sort of such experience or not.
to quote one of such experience, when I was a child, when I used to, make those paper plane and used to fly. I made first one paper plane using newspaper, and then I make using my notebook. And I have seen that this newspaper one will never fly. I mean, they will glide for a very longer distance. It is always a good shade of paper which can make the plane glide for a longer period of time. And if you use instead of that a hard shape, the plane will never fly. So I had my own experience. If teacher can build upon that, can bring those things in classroom, where I see a kind of direct relation between what physics I have experienced and what physics textbook is teaching.
Sure.
If you don't see a kind of alignment, then the problem arises.
Sure.
To end of my thing is, I remembered Dr. Feynman, while writing this textbook, those three famous books, he writes one thing, that physics is all about, say, understanding 7 statements. Those Newton's laws and Maxwell's equation, and now you can also include Fermi's theories and Fermi's equations. Yeah. So he talks about that. If the physics is only about understanding those 7 statements or 7 equations, so why don't we teach children those 7 equations? So all physics been understood, right? Then say that actually to understand those equations, you need to go through so much of journeys of experience. If you don't have, you won't be able to understand what is viscosity means, what is the friction means. So therefore this whole journey happens, and the physics, as you, my government was trying to explain that, physics goes by model by model. You can't have more general thing taken into the classroom by means of a textbook, anything. It has to have a model approach. I can't tell you about the, straight away the gases behavior in this classroom. It will take years and years to understand. So what I do that, I will take a very simple approach, how a single gas molecule will behave in a vacuum. Then I will move it to a different gas, and then the actual classroom. So if you take this kind of steps, that's how the textbook takes. The textbook always take at different levels. You can't have this Bernoulli principle. As well as I had this issue is that because you explained one or two slides, this Bernoulli principle approach to that, or Newton's second law. I was just wondering that actually can derive Bernoulli's principle through Newton's law. Bernoulli principle is nothing, it's simply representing the conservation of energy. So I was just wondering how that this thing has arises. That I do not actually understand.
That's a good point. Let me answer your question. She wants to make a comment?
Yeah, you want to comment?
Yeah.
Well, I think the mistake we make teaching physics, we don't combine intuitive thinking along mathematics that displays.
Yes.
And I think it's not easy to put in books, it has to come from the teacher most of the time. And the teachers actually process this material and they don't get it. I think the best physics class I had in high school was that the teacher complemented the material with intuitive stuff.
Yes, absolutely. This has exactly been if you didn't hear her, what she said was what was missing was the intuitive component along with what is being taught in physics. So this is exactly my problem I faced in physics. I found that the intuitive component was missing, and whenever they said consider the pendulum, consider the candle, why should I consider the pendulum? Why should I consider the candle? First of all, get it down to something which is in my ambit of experience and interest, and then get me to intuitively at least relate to it. That was what was missing.
Actually, it's an interesting point, because when you start thinking about textbooks, why not twist the whole thing around and ask if you actually instructed or taught the kids right, the kids should be able to write their textbooks. In some sense. You know what I'm saying is, their understanding and their if they can just kind of put down, okay, these are the experiments that are done, etc., etc.
That would be nice. But whether they write or not, I am planning to write this into a little booklet. This and the next 2 seminars. It's my journey in flight. So that's all, and we're bang on time.
Yeah, Ram Kumar has responded saying rather than what to teach, why we teach or what to teach in physics, he also is agreeing on how is more important than other questions. And he says, yes, mathematics have overtaken the physical phenomenon. Quantitative data is important, but theoretical calculations cannot overtake the context of the discussion we have.
So Arun, can we end now? Or we have time? So before we end, I'd like to thank both our outstation members. Okay, another 5 minutes. If there are more questions, he says we have time. Are there any questions for another 5 minutes?
Yeah,
thank you. And thank you, for 11:30 in the night for Vasu, close to midnight, Austin, Texas. So have a good night, sleep, and thank you very much, Vasu. And Ramkumar, thank you so much. I know you missed the class for me. Thank you very much, Ramkumar. Good night. Thank you. Thank you all. Thank you very much. Feedback forms. Oh, we have to give you some feedback forms. So take one as fast, please. Thank you.
In one word, magnificent.